Yeah, it's cool. You were signing pages. You would have I don't have any pages. I really very bit.
Really?
Your kids will work. People have like, right? Very special.
Okay, you can turn to page 8. Okay, so we're going to talk about summation notation, and this is to give a preview into what we're going to do with this limit definition of area. So right now we're still in approximation mode where we're using rectangles to approximate a region, but we know that it's not going to be entirely accurate. But it's still an important skill, and we'll practice a bit more with Riemann sums later today. But this is the tool that we need to eventually find the exact area under the curve. So just want to provide some notes here. So this summation notation just indicates that we're adding a bunch of terms together. Okay. And this is a shorthand way of indicating that we're adding a bunch of terms. So first, we start off with the index. That's going to be the variable. That's going to be a counter. And it's always going to increment by 1. So if we start at 2, then the next term will be 3. That plugs in, then 4, then 5, and so on and so forth. So lower bound is going to be the first value that gets plugged into the expression. The upper bound is the last value that plugs in. So this. And then your a sub I is your argument expression or your formula rule. Okay. Just be aware that this upper bound is the last variable value to plug in. It doesn't mean that there are 5 terms here. It just means that's the last value. So in this case, there's only 4 terms because we start at 2, a sub 2, plus a sub 3, plus a sub 4, plus a sub 5. And we're always incrementing by 1 to get to the next value. So here, summation of I squared plus 1 from 2 to 4. The first value that we're going to plug in is 2 in for I. So we'll have 2 squared plus 1. And we're just adding a bunch of terms together. What's the next I value? What's after 2? 3. Yep. So we're always going to increment by 1. Then 3 squared plus 1. Okay, what's next? 4. Okay, do we keep going? No, that's last. Yeah, so that's the last I value that we plug in. And then whatever that sum is, it's going to be the sum of this summation. Okay, so we have some summation rules for terms that or rules that are common. So we have summation of 1. What that means is we're just keep adding 1 over and over again. So if we go from 1 to n, whatever that upper bound is, it's going to be the sum, because if we add 10 ones together, then we're going to get a sum of 10. Summation I would be like 1 plus 2 plus 3 plus 4, all the way to whatever the upper bound is. But rather than adding them all up, there's a bit of a rule. So the rule says take that upper bound, multiply by n plus 1, divided by 2, and that would be the sum of whatever we see here. I squared would be 1 squared plus 2 squared plus 3 squared plus 4 squared, all the way to n squared. It could be 10 squared. It could be up to 50. But rather than adding up every term one by one, we have this rule that can tell us the sum of that series. And then summation I cubed 1 squared plus 2 squared, well, sorry, 1 cube plus 2 cube plus 3 cube. And then here, this is just telling us that if there's any coefficient attached to the rule, you can always push it out in front just to make it a little bit easier to kind of separate and identify the rules. Okay, so let me show you what example 2 looks like. We have summation from 1 to 8 of 3i squared plus 2. Each of these has their own rule. So I'm going to break this up into different parts. So I'm going to say summation of 3i squared plus, and then 2, I can break up 2 into 2 and 1. So I can pull the 2 out. And the reason that I'm doing this is because we have specific rules for summation I squared. We have a specific rule for summation 1. So if I can pull the coefficient out, then it's a little bit easier for us to identify what rule we're working with. So I'm going to box off the parts that we're going to use a rule for. So I have a specific rule for summation of I squared from 1 to 8. And I also have a specific rule of summation 1 from 1 to n. Sorry, 1 to 8. So we look for the rule for I squared. I squared is here. So it's going to be n times n plus 1 times 2n plus 1 all over 6. Our n value is 8. So it's going to be 8 times 9 times 17 divided by 6. So rather than having to do 1 squared plus 2 squared plus 3 squared all the way to 8 squared, we have a bit of a shortcut just by using this rule here. And then we multiply that result by 3. So it's going to be 3 times, and I'm just going to enter this in the calculator here by using this rule. So 8 times 9 times 17 divided by 6. And then summation 1 from 1 to 8, it's just going to be the n value. So that n value is 8. So it's just 2 times 8. Example 3, summation from 1 to 10 of I plus 2 quantity squared. This, we're not quite ready to identify the rule yet. Let's expand everything out. So this ends up being I squared plus 4i plus 4. I'm just imagining expanding I plus 2 times I plus 2. And now we have all these individual terms, each with their own rule. So I'm going to have summation I squared. I'll pull the 4 out for summation I, and then for summation 1. And again, I like to pull all those coefficients out in front so that we can kind of box off the parts that will be affected by the rule. Okay, we're going up to 10 for each of the upper bounds. So summation I squared from 1 to 10 will just be this rule here. My n value is 10, so 10 times 11 times 21, all over 6. That's 385. Summation I is just this rule here. My n value is 10, so 10 times 11 divided by 2. And then summation 1, that's just this rule. Upper bound is n is 10, 4 times 10. let's skip example 4 and let's go down here. Okay, limits as n approaches infinity. So let's think back on finding horizontal asymptotes. If we're approaching infinity, remember we're always comparing degrees, right? So I'm going to find the limit of as n approaches infinity of this expression. So I'm going to write this out here. So limit as n approaches infinity. Sorry, I'm going to zoom in on this. I'm going to expand all this out so I can clearly see the degree in the numerator and denominator, and I can compare degrees. So if I distribute this through, n times n plus 1 gives me n squared plus 2n all over 2n squared. If I'm doing an n approaching infinity, I'm comparing degrees. What do you notice about the degrees? Same. So ratio of the coefficients, my limit is just what? 1/2. Okay. Okay, so right now it just feels like all these are kind of disconnected, but we're just doing the background setup so that we can kind of put it all together. So let's go to the next page. Okay, so now we have I involved, this variable I involved. We're going to use the summation rule to get all this in terms of n, and then we're going to do limit as n approaches infinity. So I'm going to clean up this one piece at a time. I'm going to multiply this through here. I get 4i over n squared. Now we just want to isolate the rule that will get impacted by summation. So only that I variable is going to be impacted. So think of the 4 and n squared. Think of the 4 and n squared as something that can sit outside the rule because it's not going to get impacted by that summation rule. So I'm going to rewrite this limit as n approaches infinity. I'm going to push that 4 and n squared out in front. And that way it's just easier for me to see, okay, I'm just going to try to resolve this summation I, since that's the rule, that's the portion that will get impacted by the rule. Okay, so the previous page says that summation I from 1 to n is going to be n times n plus 1 divided by 2. So I can just replace this with that rule from the previous page. And now I can just expand this out and again compare degrees and use that to help me figure out what the limit is. Okay, what do you notice? Degrees are the same. So ratio of the coefficients, what do we get? Yeah, 4 over 2, which is 2. Okay, let's do a more involved one. This one, we're going to FOIL everything out. So I'm just going to focus on this piece here. I'm going to FOIL that out. I'll distribute this first, and then I'll worry about that 2 over n. Okay, so this is the result of me expanding that binomial squared. And now I'm going to distribute that 2 over n through. And I need to put a summation in front of each of these terms, so let's do that. And as I do that, I'm just going to try to put a summation in front of each, but pull out the parts that will not get impacted by the rule. So 2 over n is just going to be a summation 1. There's no I involved, but there's going to be a summation 1 if there's nothing remains. For the 8i over n squared, I can pull the 8 and n squared out and make it summation I. There's a rule for that. And I can pull the 8 over n cubed out and do a summation I squared. So I'm going to just box off the parts that we need to replace with our rule. Okay, so from the previous page, summation 1 is just going to be n. Summation I is just going to be n times n plus 1 all over 2. And then summation I squared So the idea is that everything should just allow us to find what the leftover is, because we're just going to compare degrees for each of the fractions and then just pull the coefficient that's going to come out of that fraction. Now, there's a bit of a shortcut here because this is a lot to FOIL out, but we know that we only care about the highest degree, right? I mean, there's going to be a term that's like an n squared and an n and a constant, but we only care about the highest degree. So I'm just going to pull the first term from each parentheses, and that will give me my first term. So 2n times n times n times 8 gives me 16n cubed. There are more terms, but we know those just go away because our highest degree is 3. So we're just each fraction, we're just going to pull the highest degrees coefficients. So this one will leave us with what? Compare degrees, ratio of the coefficients is 2. From this fraction, the only term that's going to come out of this is what? 4. Yeah, that 8n doesn't matter, right? We only care about the highest degree within each fraction. So 8 over 2 is 4. And then 16 over 6 is from the last. Add all that together, we get 26 over 3. Okay, so here's the whole point of us going through this process of summation notation and limit as n approaches infinity. The whole idea is that if we are using rectangles to approximate a region, the more rectangles we use, the better our approximation is going to be. So if you look at this picture here, here I'm only using one rectangle. One rectangle for this curved region is not going to be a very good approximation. But if I were to use 4 rectangles, I can see that much better than before, but there's still some significant gaps. Meanwhile, if I have 8 rectangles or 10 rectangles, much better approximation, but you can see that there's still gaps that indicate that we're not exactly correct. So then if we keep increasing the number of intervals and rectangles, our approximation gets better and better. So then the idea is, well, what if we can push the number of rectangles out to infinity? Then technically we're gonna have something better than just an approximation. It will achieve the actual area under the curve, right? If we have infinite number of rectangles, then every gap is gonna be filled in. And so we're gonna use this concept of limits to help us reach that infinite number of rectangles. Okay. All right, so let's look at the process of finding the exact area under the rectangle using this definition here. Okay, so let's go to page 10. I'll talk about this definition in a second. Let me just show you what it looks like if we're just using 4 rectangles. Okay, so let's say we're just using 4 rectangles to approximate this region. Okay, so this is going to be a left-handed rectangle, meaning that we're using the upper left corner to represent the height of each rectangle. And this notation just indicates that we're finding the area of that region. Okay, this is an area notation. Okay, so first, let's find the width. Our width formula is b minus a over n. So we're going to do width is equal to 2 minus 0 over 4, which is 1/2. So we want the width of every rectangle to be 1/2. And we're going to increment from 0 all the way to the end of our shaded region. So if I keep incrementing by 1/2, I get 1/2. Then I get 1. Then I get 3/2. Then I get 2. All right, so we know the width of every rectangle is going to be what? 1/2. Okay. So we can say this: the integral from 0 to 2 of x squared plus 1 dx. So that just indicates that we want to find the area of that region, but we're just doing an approximation. So it's going to be a squiggly to indicate we're just using 4 rectangles. And we're going to find the width and height of each rectangle and add them up. So the width of the first rectangle is 1/2. The height of the first rectangle is going to be f of 0, right? So I'm going to plug 0 into the function to get that height. Right now, let me just represent it as function notation. We're going to resolve that later. But right now, that f of 0 indicates if I were to plug 0 into the function, that will give me the height at that point, and that will represent the height of my first rectangle. Okay, second rectangle, 1/2 times f of what? Yeah, f of 1/2. So we haven't resolved it yet, but whatever that y value gives us, that will be the height. Next up, 1/2 f of 1, and then 1/2 f of 3/2. Right, so we're just devising a plan as to how we are going to find the heights of each rectangle. And now I'm just going to do the math for us here. So if I plug 0 into the function, I'll get a y value of 1. If I plug 1/2 into the function, I'll get 5/4. If I plug 1 into the function, I'll get 2. If I plug 1.5 into the function, I'll get 13 over 4. So that ends up being 3.75. We know that this is just an approximation. We know that this is not going to be anywhere near the exact area. But I mean, there's only, some gaps here. So we know that it's going to be less than the actual area, but it's going to be in the ballpark of what that region is actually. So there's a formula that we're going to use that can allow us to increase the number of rectangles out to infinity. And we're going to use the constant of the limits to find the area of this exact region if we were to use infinite number of rectangles, okay, which would actually arrive at not just an approximation, not just a better approximation, but the actual area. Okay, so here's what the rule says. The rule says there's a width component, just like how we did here. And then there's a f of an x value to plug into the function. But this is a formula that is incrementing to the next interval. Now, we did it manually, right? We started at 0 and we kept adding 1/2 to the next to get to the increment to plug into the function. But this is going to do the increment all by itself. It's going to increment to the next term. We just have to plug into the formula and just understand that the limit notation is going to add up infinite number of rectangles. But this is doing the job of what we just did, going from 0 to 1/2 to 1 to 3/2. But this is a counter that is done within the formula. Okay, so we're going to find the exact area under this curve using the above limit definition. Okay, so we're just going to copy. Let me copy the exact rule from above, and then we can just place all the pieces where they belong. Okay, so I'm just going to copy this down. So my A and B value will remain the same. My A is 0 and my B is 2. So we'll say 2 minus 0 over n. Before we had a set number of rectangles. Now we're going to leave that n as a variable because we do want to push it out to infinity. So we don't want to give a set number because we want more than just a few rectangles. Okay, times f of A. A is your left endpoint. In this case, will be 0. And then b minus a over n, again, that's the width times I. Okay, so what we have here is we have 2 over n. This is the width component of the rectangle. And this is the height component of the rectangle, right? F of, just like how we had it here, right? We have width and height, width and height, width and height. But now it's going to be written in a notation. And eventually we're going to push that, push the number of rectangles out to infinity. Okay, but we do see the width and height component of these rectangles that we're going to be adding together. Now, this is a plan as to how the increment is going to look, but this is not the exact function that we're using, right? The exact function that we're using is going to be that x squared plus 1. So what we're going to do is we're going to have to adapt this into the function. So whatever is inside the parentheses is going to go into the x for the function that's going to actually tell us the height at each of these points. So let me rewrite this. So my x is going to be 2 over ni. So I'm going to say 2 over ni squared plus. So now I've entered the argument into the function, and this is going to be telling us exactly the height at every point. Okay, so now that we've gotten it out of function notation, we're just going to clean this up and get that summation I resolved, get everything in terms of n, and then we push n out to infinity, and then we use comparing degrees to find the exact area under the curve. Okay, so I'm going to just expand this out, make it 4 over n squared, I squared, plus 1. So if I can just resolve this, let me clean this up here. I'm going to separate each of these into its own summation and then pull the coefficients that's not part of the rule. And the hope is that we can get everything in terms of n, and then we can evaluate the limit. So if I don't see any I, then I know it's just going to be a summation 1. This is a summation I squared. So I'll box off the parts that is going to get impacted by the rule. And we're just going to read the rule to replace them with what the rule has. Okay, so summation I squared is going to be n times n plus 1 times 2n plus 1 all over 6. And summation 1 is just going to be n. We talked about how we don't have to expand all this out. We just have to identify the highest degree term and then leave the rest alone because we know that theirs is going to fall off. So if I multiply all this out, 8 times n times 2n, what does that give me? 16n to the third, right? That's all I care about because there are going to be lower degrees, but only the highest degree pair is going to have any impact. And this is just plus what? 2n over n, just 2, yeah. So I'm just left with 16 over 6 plus 2. That's the result of limit as n approaches infinity. And 14/3 is going to be the actual area of this shaded region. So it should be pretty close to 3.75. But obviously, this should be a higher value since this is under approximation. So if you did 14 over 3, 4.6. So 4.6 is the actual area. Our approximation using 4 rectangles only gave us 3.75. Okay. This is more of a kind of a conceptual understanding of how we can use calculus to find the exact area under the curve, and we're moving away from approximation. But approximation is still going to be important. So let's go back to Riemann sums, which we briefly talked about yesterday, and that's going to be the more important one because we're going to have a much more efficient way to find the area now that we've gone through this limit definition. So if you guys can turn to page 13. We're going to go back to table of values and identify the approximations using their specific methods. Okay, so let me go through this process here. We have selected values of a function, and it's all going to be a continuous function here. It says give the middle approximation. Now, middle is in quotes. Okay, middle doesn't mean exactly in the middle. It just means that it just needs to be between our endpoints. So middle approximation with 3 subintervals from 0 to 20. So from 0 to 20, we're going to separate them into sets of ordered pairs. Now, every subinterval may be a different width, but they're all going to see or span across the same number of ordered pairs. So if I try to subdivide from 0 to 20, I'm going to say 0 to 8. That will span 3 ordered pairs. And then we're going to pick up where we left off from 8 to 12. That will span 3 ordered pairs. and then from 12 to 20. They may not be the same width per se, but they're all going to, but they're equivalent in the sense that they're all spanning across the same number of order pairs. Make sure that every time you drop down your bar there, that it's overlapping over the same order pair. Okay. Some students would do it between the endpoints, and that kind of throws us off. So just make sure you go from middle to middle each time you do a bracket for your interval. All right. When you subtract the x values, it gives you the width. Okay, and we're just adding rectangles here. So what's the width of my first rectangle? 8. Okay. Second rectangle, 4. Third rectangle, 8. So the width of my first rectangle is 8. Width of second is 4. The width of third is 8. Now, the y value is going to give you the height that we want. So it's either a middle, a left, or right. If it's left or right, then we want to use the left endpoint wherever the marks are, the arrows are pointing down. But we want the middle. So 5, I know 5 is not exactly midpoint, but for us, middle is just whatever's between 0 and 8 is the middle. So 5 is the middle order pair. So we're going to choose 2 to represent the height of that first rectangle. Okay. What will be the height of the second rectangle? Yeah, last rectangle, 6. And we're just going to add these up, those areas up. So adding up areas of 3 rectangles will be 8 times 2, 4 times 7, and 8 times 6. So 16 plus 28 plus 48. Using this approximation, we have an area of 92. Okay, you guys want to try part B? Right-handed rectangles, 3 subintervals from 0 to 20. Careful that you pay attention to your interval. It may not always span from one end to the other. Sometimes it may only span across a portion of the table of values. So always pay attention. Don't always assume that we're always going from end to end. Right now we are, but later on, we may have different starting and ending points. Same width, but we're just picking off the left y value of each subinterval. Oh, sorry, my bad. Right-handed, my bad. So 3 is the height of my first rectangle. 3 is the height of my second rectangle, and 10 is the height of my last rectangle. Okay, part C, left-handed rectangles, 3 subintervals, but here we got to be careful. What's the interval here? 0 to 9. So from 0 to 9, that means our intervals will be shorter. So 0 to 5, that will be 1, 5 to 8, and 8 to 9. Okay, subtract your x values to get your width. And pick off the left y value for each subinterval. Okay, trapezoids. Let me talk about trapezoids here. There's a formula for trapezoids, which is 1/2 width, height 1 plus height 2. Now, this is the way that I've been showing students. This is the area of each of the trapezoids, but I think this students have trouble with. And so I found a way that someone was presenting it without having to go through this formula. And I think this will be a lot cleaner for you guys to do it this way. And the idea is this: you're going to just do left sum plus the right sum, and then just average them, just divide it by 2. So pretend you're doing the left sum, then you do the right sum, and then you add them all up and you divide it by 2. I think that is a little bit easier than having to go through and memorize a brand new formula. So let's just go through this way to see how you guys feel about it. So 2 subintervals from 0 to 20. So we want to span across a lot more order pairs, but make sure that every interval spans the same number of order pairs. So the first one, I'll go from 0 to what? 0 to 9. Let's double check that. That's 1, 2, 3, 4. That's 4 order pairs. And then the other one is also 4 order pairs, right? From 9 to 20. Okay. All right. What's the width? Width is 9. Okay. Second width? 11. Okay. Let's just pretend like we're doing left sum. Okay. So left sum would be, first rectangle will be 9 times 4. Okay. Plus, what's the second rectangle if we want to do a left sum? 11 times 7. Okay, so we're done with the left, but let's keep going. We're gonna now go back and do the right sum. Okay, so go back to the first rectangle. 9 times what? 9 times 7. And then 11 times 10. So we're adding up the left sum and the right sum, and then we're just averaging them. So divided by 2, and that will be same thing as adding 2 trapezoids. I find that I think this will be a little bit cleaner. Sometimes when students go through this process, sometimes students will either forget to add the heights or they would get the width wrong. And I see a lot of students in the past have trouble with this. So I'm thinking maybe this will be easier. Just think of it as, okay, I'm just doing left sum and right sum, add them all up and then divide it by 2. I'm just averaging between my sums. So I get 143. Okay. Can we try number 2? I just want to walk around and just see if this makes sense. I think this is an easy process, but saying that though, a lot of students have trouble with the width and height. Sometimes students want to add the numbers together, or they would do the subtraction for the y value, and I feel like if I can just walk around and help make some corrections, then hopefully this will be an easy process for you. So if you guys can try number 2, and I just want to see you guys try the first 2, just so that I can see that you're understanding how to pull the width and understanding how to pull the height. Again, middle is just in quotes. It's not, we're not doing anything with averages. You're just literally picking whatever is in the middle of your order pair of your interval is the height you want to choose. So 7 is not the midpoint between 1 and 12. It just happens to be amongst those 5 order pairs is the one that's the most middle. So we choose the one that is quote unquote most middle. But whatever Y values you get is what Y value you're gonna use. You're not going to have to do any calculations of averaging any numbers together. Okay, so tomorrow I'm just gonna check page 13, see if you guys can get comfortable with that, and then we'll move on.